Here's an example of a fourth degree equation we would like to solve. Now, we've already looked at a technique that we could use to solve this kind of equation. If you've looked at the other videos, the previous videos, you've seen the technique of making a substitution, substituting some value in order to create what we recognize as a straight quadratic equation where one of the variables will be squared, the other term will have a variable to the first power. So we could use that substitution technique to solve this equation. We could do something like this. We could let y equal x squared. So then this term would become minus 10y. Well, if we let y be x squared, then wouldn't y squared equal x to the fourth? If you square x squared, you'd have x to the fourth. So I could replace this term with y squared. And that would create a quadratic equation that we know how to solve. And once we got that solution, we could then set x squared equal to that solution, and we could then find what x actually was. That's a substitution technique that I've illustrated in some of the other videos. In fact, let's go ahead and finish that out just to illustrate it with this equation, and then I'll show you a different way we could actually solve this equation, by factoring. So if we solve that equation, and that's a nice trinomial. In fact, it's so nice, it's a factorable trinomial. In fact, that's going to factor into y minus 5 times y minus 5, isn't it? Y times y is y squared. Minus 5y minus 5y more gives minus 10y. Minus 5 times minus 5 is plus 25. So the two solutions we'd have here is y equals 5, y equals 5. We actually have identical solutions, don't we? But y was just holding the place of x squared. So we now substitute back. X squared equals 5. Well, that's a quadratic equation that I can solve by the square root property. Something squared equals a constant. So the something being squared, x, is equal to plus or minus the square root of the constant. So the solutions to this equation are positive and negative square root of 5. And that's the exact solution. I can't simplify the square root of 5 any further. So that's one technique that we've seen illustrated before, that we can make these substitutions. But I want to show you that you could have solved that equation without making the substitution, just by factoring that trinomial in its original form. If you're going to take the product of two binomials and get a minus sign here and a plus sign here, that has to come from two minus signs in your binomials, two subtractions, doesn't it? And how do we get x to the fourth? Well, couldn't we get x to the fourth by x squared times x squared? And couldn't we get 25 with 5 times 5? And wouldn't the O and the I of FOIL give us minus 10x squared? This would be minus 5x squared, minus 5x squared more, that's minus 10x squared. So that trinomial was actually factorable. We normally think of just factoring when we have a second degree trinomial. That's what we're used to with factoring, but we can actually factor a trinomial sometimes, not all times. Just like with any kind of factoring, you can't factor every trinomial. Some trinomials can be factorable when they have a higher power than 2. And now we can take that same thought process. What could you square and subtract 5 from it to make 0? Well, let's just set that quantity equal to 0 to find out. And here's our quadratic equation that's missing the first power term. We can solve that with the square root property. X squared equals 5, so x equals plus or minus the square root of 5. And the solutions from this factor would be identical. So here's an alternate way of finding the solution to this equation by examining that trinomial and recognizing that it was actually factorable in its current form.